Do you have the lecture sheet of the last lecture? PDF of last lecture? Have I shared before the last lecture PDF?
No,
No.
sir.
So it was on what date? Do you remember the date?
Twelfth April.
12th April. Yeah.
No, no, sir. No.
Maybe 12th.
Sir, you didn't share the PDF.
So you remember the date? The on which date it happened?
Sir, it was after 12th April, but I don't remember the date.
So maybe on 16th. 13th. Uh, let me see. I think the date you don't remember. Try to search here. I think this was the it's very small 13th. 13th I'm not coming. 11, 12, 13, I've seen this. Hello, hello. Hello, hello. Am I audible, guys?
Yes.
Okay. So in case of progressive wave, if I call this as the x-axis, and if I assume that the wave is maybe produced at this instant, and then it is moving ahead. So if it is traveling wave, it means as the time will pass by, it will move forward. But in moving so, what remains same is the shape. So nowhere, no matter where the wave has reached or arrived, the shape remains the same. So maybe after some time, the wave will appear here. And we assume that the medium is non-dispersive and the property of medium is maintained throughout the journey. So the wave velocity, which is the property of medium, will remain the same. So it will keep on moving with velocity v. So after, let's say if this is the time t equals to 0, the first one, then this may be some time t equals to t. So the graph will keep on shifting towards the right. If I draw another axis, and if the axis itself is moving with velocity v, then in frame of this coordinate system, which is x dash o y dash, in this frame, the wave will never appear to be shifting. So what we can say that the equation of this wave will never shift in this frame, whereas it is shifting in the frame at rest. In the y-x frame, it is moving, but in the y dash x dash frame, it is at rest all the time. And why it is happening? Because the frame is also moving with the same velocity as that of the wave. So definitely we can say after time t, the frame will shift by how much value? Vt. Now we have the new coordinate system x dash o dash y dash. So every shape in a two dimension we can call as a graph, and every graph will have the definite relation between the two variables y and x. If I choose some random value of x dash comma y dash in the frame of x dash o dash y dash, so this distance we can write as x dash, and this we can write as y dash. Do you realize this? What I'm saying? Now, if you try to measure the same coordinate in the x o y frame, then what is the y coordinate of this point? So you can clearly see the y coordinate is same as the y. So whether you're trying to find the y coordinate or whether you're trying to find the y dash coordinate, there is no difference in the y dash. So this is y. But if you try to find the x dash, then if you try to find the x value, the x coordinate of this point, you can clearly see the x coordinate is how much? Vt plus x dash. So x coordinate is basically Vt plus x dash, and therefore the x dash we wrote as x minus Vt. So equation of graph, because in the y dash x dash o dash frame, we can write y dash equals to f of x dash, because it is not shifting, it is like a fixed shape. So we can write like this. So y dash is equals to fx dash is a graph. Now we know that y dash is equals to y, but x dash equals to x minus vt. So this equation can be rewritten in terms of the original coordinate system y equals to f of x minus vt. And here we have assumed that the wave is moving towards the x-axis. So what you can see, if you are moving towards the x-axis, the minus will appear. In a similar fashion, if we have a coordinate system, and if the wave is traveling towards the right, sorry, traveling towards the left, then after time t, it will shift towards the left. So if I draw a frame, let's say like this, and if I say that this frame is moving towards left with speed v only, then the graph will remain the same. So every point here, so if I try to plot the point here in the y dash x dash, this will be some negative value. So the coordinate will be how much? This coordinate is how much? Let's call it minus x dash minus x dash comma y dash. So the x coordinate is how much? If I want to write the x coordinate value, so so a general expression for traveling wave we can write as y is a function of x comma t, and this x comma t should be in either plus vt or minus vt, or this could be written as vt plus minus x. Now you can choose whatever term to write first and the term second, but the sign between these two terms will decide the direction of motion. So the role of plus or minus sign in between only is to decide the direction of motion. So what you can write here as a note, the sign between x and vt decides the direction of motion. Okay. So if it is minus sign, so if we have the negative sign between x and vt, then the wave is moving towards the positive direction of x-axis. We can say then wave is moving in the positive direction of x-axis and vice versa. Which means if the sign is positive, then the wave is moving towards the negative axis of, negative direction of x-axis. Other thing which we need to understand, so how to represent the standard equation of wave equation. So what we mean by standard equation? So standard equation means no matter which wave we talk about, whether it's a traveling wave or any random wave, all will follow this differential equation. So basically, it is a differential equation followed by every wave. So if I have the equation y equals to f of x minus bt, or you can take x plus bt. So it's called the multivariable function. So we have two types of variable, and in case of multivariable function, we do use the partial derivative. So del y by del x, or del t of 102 values. So del y by del t will be how much? So to differentiate with respect to time t, you can use the chain rule. So first differentiate the function, whatever it is, and then differentiate the argument of function, which will give you partially minus b, because if you differentiate with respect to time, x will be constant, and therefore what we will get is minus b. So now if we try to differentiate with respect to x, what we will get? F dash x minus bt, and then if you differentiate the argument of function, it will give you 1, because x differentiation is 1. So if you compare these two questions, you can clearly see that that del y by del t is minus b del y by del x. This is what you can see. And the term on the LHS, the left hand side is the y is called displacement of particle. So displacement of particle with respect to time, the rate of displacement of particle with respect to time, we can call it velocity of particle. And we can clearly see this is minus b times del y by del x is the graph of y and x, and this is called the slope. So particle velocity depends on the wave velocity multiplied by the slope of the graph between y and x. If you start from the equation on the right side, there is a small change in the derivation, and instead of minus sign we will have a plus sign. And rest no change you will see here, and therefore the relation will be so. Definitely this is also a differential equation, but this do not represent the standard equation. The reason is, by taking two different directions, we have two different signs, so we cannot call this as a differential equation or standard equation, because it varies from equation to equation. So we have to do something which is independent of this direction of motion. And to do that, we have to differentiate once more. So if you differentiate the second term del 2y by del t square, which is also called the acceleration of particle. So you can go back and you can check the first derivative is f dash x minus vt minus v. If you differentiate once again, minus v will come again. And what we'll get is v square f double dash x minus v. And if you differentiate the x second term, you will only get f double dash x minus vt. And which is also true for the other direction. Now you can choose anyone and you can see the final answer is same. If I substitute, I can clearly see the second derivative of the time, the acceleration is square of the velocity into rate of change of slope. So it's a second order differential equation of time and position. And this comes same even you choose the second format. And because this answer is independent of the direction of motion of the wave, there's a unique format here. So this equation in physics we call the standard wave equation. So we can write like the del 2y upon del t square, which is like the acceleration of particle, is the square of the wave velocity. Now v is called the velocity of wave, not particle. But del y by del t is called velocity of particle into second derivative of y with respect to x. This is called standard wave equation, and this is although we derive from the traveling wave, but this is true for all sort of waves. So whether we have standing wave or any other wave, it will follow this pattern. Okay. So now this is the standard wave. So let me show you some examples how to use these equations. So if we have if I draw a sinusoidal wave, and let's say this wave is traveling towards right, and y is the displacement of particles. So what you need to realize that these particles are displaced from this position. So this is the y, whereas the wave is moving towards x-axis. So if you draw the graph at a later instant, slightly ahead, I mean maybe after time dt, the graph will appear something like this. And there is something you can guess. So what you can guess that every particle before this line, the midpoint, everyone is going towards down or up. You can check how they're moving downward. But every particle beyond the midpoint, you can see they are moving upward. and every particle again particle after this is again moving down. You can change this. So what I'm trying to explain that if a wave is moving towards the right side, you can exactly tell that how many particles, like what range of particles are going down and what range of particles are going up. And this can also be said by the formula. The del y by del t is minus v del y by del x. If you remember the formula, if you are going towards the right, this is the first order differential equation for this wave. So velocity of particle will have minus velocity of a wave into slope. So if the wave is moving towards the right, we can put a v equals to positive value minus, and we have to just look for the sign actually. So the velocity is positive. So if you choose any point before this point, so if you draw tangent anywhere, so every tangent will be acute, and therefore every point before the midpoint will have the positive slope, and therefore you can see the sign of the particle will be negative, which simply means that they are going downwards. That's the meaning of negative. But if you try to draw the slope of any point beyond the midpoint, they will make the obtuse angle with x-axis, and so their slope will be negative. And if you try to use the same formula to find the VP with a positive direction of velocity and negative slope, the answer will be positive, which means they are going upward. So simply by using the relation and substituting the sign, we can also get the answer. And we can also get the answer more organically by shifting the graph towards right by a small value. And then organically you can check whether they are going left or right, up or down. So this is the first application of this. So if any mathematical function is written in the format of standard equation, you can easily find the wave equation. So later on we will also derive. So let's see if I say that del 2 y by del t square is equals to t1 mu del 2 y by del x square. So our standard equation says that the second derivative of this is v square times. So if you compare equation 1 and 2, you can clearly see the v square is nothing but t by mu. So v equals to t by. So in fact, most of the formula that we will derive about the velocity of wave, we have to use the second order differential equation, which is easy to do it mathematically. So we will learn how to do that. Okay. So The next part that we are supposed to do is called the traveling wave for equation of plane progressive sinusoidal wave. So now we are looking for those waves which are having sinusoidal behavior. So they are periodic and sinusoidal, and then we are trying to find their equation. So there are many ways to derive the equation. So every sine function. So let's say if this is the displacement of particle. So the height, what you see, the way to interpret is like these are particles. So these are particles, and what you see is called the snapshot. Like it is a picture taken at some random instant. So these the dots are the original location of the particle about which they will oscillate. And assuming it's a transverse wave or whatever wave, longitudinal wave, these are the magnitude of displacement. So it is not specifying whether it's going up or down. This is only the value of displacement from the mean position, which may be right or left for longitudinal wave, which may be up and down for transverse wave. So do not interpret this as transverse or longitudinal wave. This is just a displacement relation of these particles. So how much they go up or down or left or right. The magnitude we are plotting here. That's the whole idea. Now the property of traveling wave is that every particle will have same display, I mean same amplitude of oscillation. It means eventually every particle can go up to the same height because the wave is traveling. So the peak will cross every point, isn't it? So this peak will be here also, here also, here also. Peak will be everywhere. So no matter which particle you choose, all will eventually attain the same amplitude of oscillation. So the first thing that we need to remember about uh, progressive wave, that each, and I'm talking about the plane progressive. So there is a meaning of this. So when I say plane progressive, it means the amplitude remains constant during the propagation, and therefore every, so in case of plane progressive traveling wave, plane progressive wave, amplitude remains constant. So every particle will eventually go to the same displacement or will suffer the same amplitude in the subsequent motion, no matter which particle you choose. So everyone will have the same amplitude. So A is a fixed value. If it is plane progressive, that's the property. Okay. So the question is how to derive the equation of such wave. So first of all, every, if it is a sine function, so it will have some equation. So you can derive by the method one. You can use the graph shifting method. So the way of writing the equation will be y equals to, let's say y, the the y of the wave at any point x, but at t equals to 0, if I call let this is given by the formula a sine, and we write kx. And what is k here? The value of k we write as 2 pi by lambda. So let's say this is the sine function a sine kx, and what we know that at we are trying to write a equation of x comma t, that at any instant of time t. So if you remember, at any time t, the x will be shifted by x minus vt. So this x must be transformed into this value to get the generalized relation of y of any particle at any location at any time t. So the idea is, if you know the answer for one instant, and specifically, let's say if you know the answer at t equals to 0 or any instant, then finding the answer for a general instant of time is or can be obtained by simply shifting the x coordinate. So we have to shift x by x minus vt, and we are done. So this equation will look like y x comma t is a sine kx minus vt, and we can further write as kx minus kv into t. So from the concept of SHM, so we can assume every particle. So here what is happening is every particle is performing basically SHM. So every particle will go up and down, so they will perform SHM, or right or left. So in case of longitudinal wave, the point will move left or right, and this we call amplitude of oscillation on both sides. So every particle is performing SHM, and we have infinite SHM taking place simultaneously along the line. So you can say a traveling wave is nothing but a oscillation of infinite particles at the same time. So every particle will move in a circle. So corresponding to their motion, we can define the omega, and we know that omega is defined as 2 pi by time period. So t is the time period of oscillation, and k is defined as 2 pi by lambda. So from the definition of wave velocity, which is defined as the lambda upon time period, this we can rewrite as, so you can just write like this. Lambda is Vt, so 1 by lambda is 1 by Vt, just invert it, and then multiply by 2 pi. So 2 pi by lambda is 2 pi by V into 2. But 2 pi by lambda by definition, we call it K, and 2 pi by omega, we call it omega, 2 pi by T, we call it omega. So basically the formula is K equals to omega by V. So you just need to know all this simple relation. Omega we can write as K into V. And therefore the expression here we can simplify further as a sine kx minus omega t. Now whatever is inside the bracket is called the argument, or I mean the angle or the phase. So we can call it argument, angle, or phase. And you can see the phase of the sine function depends on position and time taken. So the equation of sinusoidal wave can be written in various ways. You can write as a sine, and we can replace k and omega by 2 pi by lambda. So you can write 2 pi common. So this will become x by lambda minus t by capital T. So these are again various format to write the same thing. Now what you are supposed to remember is that anything which is multiplied with x will represent k. The whole thing multiplied with x is k, and whatever we multiply with time t will represent omega, and that is how you have to compare and get the values. No need to worry about the way of writing. So in the above box, in the box number 1, what is the coefficient of x? It is k. And what is the coefficient of t? It's omega. But if you come to the below box, the coefficient of x, if you look carefully, is 2 pi by lambda and t is 2 pi by t. So that is what you have to identify, the coefficients, and then you are done. So this is how we can write the equation of sinusoidal wave simply by shifting. Okay, the graph. So this is the method 1. We can do the by other method also. So this next method is called method 2. So we call it time shift. So we shift in time. So imagine the situation like this. So a traveling wave is nothing but the infinite SHM. So imagine a particle at origin which is performing the SHM. So this particle is performing SHM up and down, or you can think the right or left, doesn't matter. So let's say this is the particle at which position? So this is the particle at x equals to 0. Now, if I try to write the equation of SHM of any particle, and I hope you remember the SHM, equation of SHM of particle at x equals to 0 as a function of time t, you can write as a sine omega t plus phi, where phi is the initial phase. So this is the general equation of SHM. Phi can be 0 or non-zero depending on whether you start from the mean position at the time of observation or you start from somewhere else from the, at the time of observation. So phi can depend, phi will depend on the initial phase. So like from where you start your motion, or the t equals to 0, you may be at origin or may not be at origin. So wherever the observer sees you at t equals to 0 will decide the phi. But this is the equation of SHM of a particle at the origin. Now, if I assume the wave is moving towards right, the wave is moving towards right. So this particle has started the oscillation, which is at the origin. Now, my question is, when this particle will start the oscillation? When this will start? And I'm saying this particle is at a random location x comma 0. So any wave traveling or any wave which is starting from the origin will reach at this location after what time? So time taken to reach here will be x by v. So x by v is the time that the wave will take to reach here. Okay. So if the particle at the origin has been oscillating for time t, so at t second, you can look this way. So if t is the time of oscillation of particle at x equals to 0, then for how long the particle at x equals to x must be oscillating. Now try to realize this part what I'm saying. The particle at x equals to 0 is oscillating for time t, and we're trying to write every answer in terms of the origin only. So the particle at origin is oscillating for time t. Let's say for last 10 hours, the particle at origin is dancing. Upon hearing the music, he is dancing. So music is the wave, and because the wave is traveling towards the right, so who will listen to the music first? The particle at 0 or the particle at x? Tell me. So imagine if I have placed the speaker at the origin. The moment you switch on, the wave will travel and will take some time to reach the other point, right? So which point will hear the music first? No idea.
Origin.
Origin. So if a particle is located at a distance x away, then after what time that guy will hear the music for the first time? If the location is x distance away, so the music will arrive at the point x after time x by v, isn't it? Not
Yes.
getting right. So if the time taken by the wave itself is to reach the particle is x by v, then out of the time t, this much time has taken for the wave to come here, and then for the remaining time only the particle will oscillate, isn't it? Because the particle will start the oscillation only after hearing the music. Music is coming at the point after time x by v. So the time which is left for you to dance is how much? Let's say the DJ club will shut down at 10 p.m. or maybe 11 p.m. So a guy is arriving at the venue at 6 will get 5 hours to dance, but the guy arriving at 7 will get only, I mean, okay, what I said, 6, 5, 11. And if you arrive at 8 o'clock, then how much? Just 3 hours. If you arrive at 9 p.m., then you will only dance for 2 hours, and so on. So a particle at a position 0 is dancing for t time, then a particle at x equals to x will dance for how much time? No idea.
X by
Hmm? Array t is the total time for which the particle at the origin has been dancing. So for how long the particle at x must be dancing? And the whole idea is that the
T minus
dancing,
delta T.
yeah, t minus delta. That's simple answer. Why are you waiting for so long? So the particle at x equals to x will only dance for t minus the time taken by the wave to arrive at the particle, because for that duration he is not dancing. The reason is there is no music. So the equation, see, let's say you know this equation. So I'm saying that the equation of this point is a sine omega t plus phi. So what we are trying to write the equation is, what about this point? So what is the equation of this point? The answer is a sine omega. The only difference is t will be replaced by t minus delta. The rest will remain same. Nothing will change. Are you getting the idea what I'm writing here? And therefore, the y will become a sine omega t t minus x by v. You can ignore the plus minus 5 to make it simpler. In the previous case, I mean, I just ignored the 5. But even if it is present, no need to worry. This will represent the initial phase. So the displacement of the particle, y represents the displacement of the particle. Now we have the answer in general. So omega multiplied by t minus x by v plus 5. Let's put in bracket. How to put this? Like this. And further, you can write omega into t minus omega by v. So if you do so, so it becomes omega t minus omega x by v plus 5. And again, if you go back, omega by v is what? Omega by v is nothing but the k. So all will lead to the same answer. With switching of the side will not affect the answer. So if omega t comes first and kx comes afterwards, it really doesn't matter. What matters is the sign between them. So in the previous derivation, we had omega t, I mean kx minus omega t. Now we have omega t minus kx. But both are equivalent because the direction is decided by the sign between the term, not the position of term. So it really doesn't matter whether I write kx first or omega t first. So the whole idea is we can shift the time and we can get the new equation. So what you are supposed to know or understand is that if one equation is given, how to shift in position and how to shift in time. Okay. Now the third method is very important, and this is called the phase shift method. And this method again we can use in two ways: either phase shift due to position or due to time. So again, this will have two due to position. So let me show one by one. So what we need to understand for this situation is the idea of phase, and we will learn about the lag and the lead concept of phase. So there is a concept of phase called the phase lag and phase lead. So let's say x is representing the location of particles which participate in the wave propagation, or you can say the wave will pass through these points. So these are the locus of points through which the wave will pass. And this is 1, this is 0. Now what we need to realize that a large number of particles are arranged along the x-axis, and these are the points, and wave will move either right or left. So I am okay, I'm just taking the wave, and the motion of every particle will only begin once they receive the wave for the first time. So how to relate the phase concept in case of wave? So first of all, we are trying to learn in terms of position. So let's say we have a 2 points, one or two particles, one at x equals to x1 and other is at x equals to x. So we know that if we have a wave like this, So if I choose the particle here and if I choose the particle here, their separation you can clearly write as lambda. So on a circular scale, these two particles are separated by an angle of 2 pi. So if you start from a position, if you come back to the same position, you have to turn by 2 pi. So 2 pi is called the phase difference and lambda is called the path difference. And there is a one-to-one relation between the path difference and the phase difference. Just
The call from Vandana
Am I audible, guys?
Yes.
Hello, hello. So every particle on a kept on a medium will have some path separation, and we call it path difference. And every path difference we can correlate with the phase difference, which is the angular mapping of path difference. So we all know that when you make one oscillation, you turn by 2 pi, which is as good as traveling by lambda. So both are equivalent in terms of phase. So what we call it, that a path difference of lambda, path difference of lambda is equivalent of 2 pi phase difference. It means if two particles differ in phase difference by 2 pi, then it means they must be differing in the phase difference, path difference by lambda. So lambda length is equivalent of 2 pi phase difference. So a length of 1 unit is equivalent of a phase difference of 2 pi by lambda. It means if the 2 points are at a unit separation, then the phase which they create, the phase difference which they create is 2 pi by lambda. That's the whole idea. So when I say if two particles are at a separation of delta x, then the phase difference that they will create will be 2 pi by lambda into delta x. Now, because of the appearance of the term 2 pi by lambda very often in this subject, many physicists thought of giving it a name, and this 2 pi by lambda is kind of a angular analogous to the wave number. So this is like a, so this is called angular wave number, and this is what we call k. So if you remember from chemistry, 1 by lambda is called the wave number, which gives you the idea that number of wave per unit length. Number of wave per unit length. So you can just think of 2 pi is making it a kind of angular analog only. So this is not something having physical meaning, but this is just written like this. So 2 pi by lambda we can write as angular wave number or simply k. And that is the reason that any 2 point in space at a separation of delta x will create a phase difference. So phase difference between 2 points at a separation delta x will be k delta x. So now the question is, what is the meaning of lag and the lead? So the whole idea is, if a wave is traveling towards right, then the one which receive the wave first will lead, and the one which will receive the wave later will lag. That's the whole idea. So if I assume the wave is traveling towards right, then which particle will lead among, I mean, between this x1 and x2? So who will lead and who will lag? So we can say x1 will lead and x2 will lag by the phase difference of how much? A delta x. Now what does it mean? So if I say the equation of this particle is A sine omega t, just I'm writing. Maybe you can say phi. So if I'm giving you this equation and if I'm asking you what is the equation of this particle, so given this, find y. The answer is simple. Just look at the separation. They are at a separation x2 minus x1. So the phase difference between these two particles must be k delta x, and it must be lagging behind the first particle because the wave is traveling towards right. So he will be the second recipient of the wave. The first one is the first one. And because it's easy to write the phase, because this is phase only, so the angle is called phase. So just write the answer, and because it will lag, we'll subtract the phase difference, which we have got how much? K times x1 minus x2 minus x2. So value. We have to add the value only. So you can see it's very easy to write the equation. Once you know the equation of any one particle, the other particle will have to write only in terms of phase shift. So what we are shifting is the phase, because in sinusoidal function, it is easy to understand the phase relation. Okay. So if any wave is sinusoidal, or if we have a periodic wave with a finite wavelength, then the phase relation will help us in getting the answer. So if we know the answer for x1, we know the answer for x2. I hope this is clear. So this relation is very,
Yes.
very important. The phase difference is 2 pi by lambda into path difference. So you can just write like this. Phase difference equals to 2 pi by lambda into path difference. So knowing the position is sufficient to tell us about the lag or the lead. And how to decide the lag and the lead? So I have told you. So in the direction of wave propagation, in the direction of wave propagation, the particle which comes first relative to another particle, so the particle which comes first relative to another particle is said to be leading, and the other is, and you can say other is said to be lag. Okay. So you can see that we have made the shift of, so you were knowing the location of two particles x1 and x2, and the moment I give you the equation of first particle, it's very easy for you to write the equation of second particle. So let's apply this concept to solve the question which we have already solved many times, just one more time. So if the wave is traveling towards the right, and if this particle which is located at the origin, imagine this particle oscillating at the origin, and if I'm calling the equation of this particle as a sine omega t, that's simple. I'm not writing phi. So can you tell me the equation of particle at x comma 0? So what will be its equation? So you already know the equation of particle at the oscillating at the origin. You're supposed to write the equation of particle at any position x. That's it. Tell me. So you have to only shift the phase. Who is lagging, who is leading? Just if no, it's lagging, subtract. If it is leading, add. Hello guys, am I audible now? Hello, 1 2 3, 1 2 3. Okay. So what I was saying is that if the particle at x1, we know the equation is a sin omega t, and now we are looking for the equation of particle which is located at a position x2, and the gap is clearly seen. So if I'm saying that if the wave is coming at x1 at time t, then after what time the wave will arrive at x2? So the answer is x2 minus x1 by v time later. So there is a time gap of arrival. So we know that if the first particle and this, if I want to know the first particle and second particle difference, if the first particle starts here and second particle may start somewhere, we don't know where they start. So if the first particle starts at some location, okay, I'm taking here 0 1 because the way I'm considering is omega t, so no phase. So the first particle is here. Now, by the time the wave will arrive at the second particle, the first particle will turn by what angle? That's the question. So, if I know this is the time gap is, if I call the delta t as, so the second particle will only start moving after delta t. So, by the time the second particle will start, the first will be here, and the angle between them will be omega delta t. So the phase difference as a time function, we can write as omega delta t. It's the same thing. And because we know the phase difference, which is omega delta t, so the equation of the particle 2 will be a sine omega t minus, because it will lag on omega t minus omega delta t. And now if you substitute the value, you can get the answer like a sine omega t minus, and again if you remember that omega by v is nothing but the k. So it is pretty easy to write the equation by shifting the, so the phase shift we can write in two ways, either omega delta t or k delta x. It is, the choice is yours how you want to write. And nevertheless, which method you use, you will get the same answer. And that is why the last question, the last derivation. So now again, if I tell you that the equation of the particle at the origin, if the equation of particle at the origin is given by y equals to a sine omega t, so can you guess the particle at any location x comma 0? Tell me what was the question. So the answer will be a sine omega, and you can add t minus x by v. That's the same thing, the shift of time. You can, okay, it's the same, everything same. So this is a sine omega, you can take common t minus omega. So it's same thing. Only the t is replaced by t minus delta t. So the way you write looks different, but all will lead to the same answer. So these are the various methods by which you can write the equation of a wave. Once you know the answer for the one, you can add the answer for the other. So sometimes it is easy to shift the phase. Sometimes it is easier to shift the time shift, phase shift, position shift, or graph shift. So the way you understand mathematics, you can apply and get the answer. So before we proceed further, we need to practice so that I can be assured that you have understood this concept. So let's go back to the chapter of wave and sound, and the question that you are supposed to solve right now are page number 324. I hope everyone is there. Okay. Yeah, SCV. From SCV page number 324. So now we start from question number 4 and solve till question number 7. That's only shifting of graph problem, and you can interpret the equation and graph. So solve from 4 to 7 as of now, then we can solve later on other questions. The rest are very easy. This chapter is one of the easiest chapter, and you can solve all the 57 questions at one go. After learning theory, it's very easy, but not now. Just formula. We have some sort of, number of formulas we have to apply. Question number 4 to 7. So if you go to page number 324, you will get only one exercise, not two exercises. So don't get, you will not get confused. Am I audible? Okay, fine. So solve 4 to 7 just right away. Then we'll solve the rest.
Done, sir.
So all done.
Yes, sir.
So all are simply based on the shifting of graph. So you have to shift one way or the other, you get that.
Yes, sir.
So now once you know the equation of wave, once you know how to shift the graph, you can do the motion analysis quickly. So we know how to find the velocity, how to find the. So you should not be confused between the velocity of wave and velocity of particle. So what y represents in the formula? The
Amplitude.
instantaneous acceleration of particle with respect to mean position. So when I write y equals to a sine omega t minus kx, the y is only representing the instantaneous position of particle with respect to its mean position located at a position x at a time t. So that's the meaning of the equation the way we write. So x is the particle at x at time t will have y displacement. That is the way of writing. So finding the velocity of particle means differentiating y with time because it's a multivariable function. So we use the partial derivative to get the velocity of particle. So Vp we can write as del y by del t, and if you differentiate with time, you get the answer a omega cos omega t minus kx. If you want to know the acceleration of particle, then differentiate once more. You get minus omega square a sine, and the kx really doesn't matter because what we are doing is the partial derivative in time, so the x will be acting as a constant. So no need to worry. And this is quite similar to the SHM. The only difference is earlier the kx was not there. Now we have kx, and why we have kx is simple because we are dealing with all particles taken together. So earlier we were dealing with one particle at one time, so x was something specific, so we were not writing. And now the progressive wave represents the description of a generalized particle of the media. That's why we have the x term. Similarly, we can do the energy analysis. So we can do the energy of. So there are two types of energy: kinetic energy, and the way we are going to analyze here that if we assume that if we have a sinusoidal wave, it will continue. So imagine it's like a thin rope, and this is a medium. So the volume of this rope is like a medium, So now we have this kinetic energy, and so when you try to, let's say you just may give a jerk to this, maybe this is a rope you are moving up and down, creating the sinusoidal wave. The energy will propagate through the medium this way, and the rate of energy propagation is always called the wave velocity. Now, when we derive the various formula, there are some underlying assumption. And what are those assumptions? The assumption is that the amplitude is very, very small. So lambda along the rope is same as the lambda along the x-axis, because the reality is the wave is not actually assumed like this. We assume the wave to be almost something like this. So the amplitude we assume in the range of millimeter or fraction of millimeter. So generally we keep it as a fraction of millimeter, I mean, even less than millimeter. And therefore, essentially, it is like a straight line. So the energy will travel in one time period lambda ahead. So basically, you can think that the rope, lambda length of rope will contain the energy which was supplied during one time period of oscillation. So we are continuously supplying the energy, and if you supply the energy for the time period t, it will, by the time end of the time period t, it will spread out up to distance lambda. That is the whole idea. So there are two types of analysis. Either you try to find the average energy for the time t, capital T, or you try to find the average energy of the particles spread over the lambda. Both will give you the same answer. So there are two analyses. One is called the time analysis, and another you can say position analysis. So if you only look at the single origin particle, so let's say if we have a, so energy, we have to find the average value. So let's say if we consider the particle only at the origin, which is oscillating, so the energy that it will receive on an average in the duration of t, delta t equals to capital T, will be equivalent of energy of the string, or you can say all particle at any given instant. So if I just take a snapshot, like I just take a picture at some instant, and I get these many particles at different locations. So what I'm saying is that the particles in the lambda length, so if I add energy of each and every particle up to lambda length, it will have the same average energy as the average energy of the particle at the origin received in the time capital T. So that's the whole idea of energy propagation. So let me write down the formula. So let's say if I move x and cut a small particle dx, so dx is a particle basically, and if we have a string, so we assume something called mu, called the linear mass density. We don't take lambda as the linear mass density. The reason is lambda is here wavelength, so that's why we have to change the symbol. So we use the symbol mu, which is the like linear mass density, that is mass per unit length. So if you cut the particle which is located at a position x, having length dx, so that we can find the mass, so the elementary kinetic energy of the particle will be half dm into v particle whole square at a location x. Okay. So we can rewrite as half mu dx, and velocity of particle can write as del y by del t whole square. That is how we write the equation. And del y by del t is easy to find. So 1 by 2 mu dx. So we are finding for the uh, oscillation of string actually. So del y by del t. So y we can write as, let's keep it simple, a sine omega t minus kx. I'm assuming the wave is moving towards right. And so the del y by del t will be a omega cos omega t minus kx. So we can substitute the value, we'll get a square omega square cos omega t minus kx. Okay, so this is the square. So this is the kinetic energy of a random particle. Okay. Now the whole idea is, if I choose the particle at x equals to 0, so take particle at x equals to 0. You can choose any particle, but that's easy to calculate. Mathematically, it's easy. Then dk we can write as mu dx a square omega square. And because I'm putting x equals to 0, so this formula is cos square omega. So now I'm getting a time function. So, but here we have x, so we can convert this into time. And the way to do is the velocity of wave. Now this is very important. So you write a velocity of particle as dy by dt. So what is the velocity v itself written? So the v is written as dx by dt. The rate at which the energy propagate along the x-axis is called velocity of wave, and therefore you can always convert the dx as v dt. The formula will change into v dt. I'll add one more step. So this turns out to be half mu a square omega square into v, and we have cos square omega t into d. So what we are trying to understand is the energy on average. So what is the average energy received? So the average energy received, so how to add the average energy? This is the power basically. So you can think this way as a this is also nice equation. Just remember the equation I'm writing the next page. So the decay turns out to be 1 by 2 mu a square omega square v into cos square. So we can write as dk by dt as now this looks like a function. The dk by dt we can think as a function, and this is basically called the power because the rate of energy flow is through power. So we can convert this into kinetic power. So we can call it, let's say this is kinetic power, and the formula is 1 by 2 mu a square omega square v into cos square. So I would like to know the average kinetic power. What is the average value of kinetic power? So now we have a relation. So this is how we can convert something into average value. So what we are trying to understand is the average kinetic power. Okay. Because once we know the average value, we can multiply with the time period to get the total, the average energy supplied in one time period. So the average value of this function means average value of this function. So the rest are constant. And what you know, like what you just need to know that the average value of
Call from +9193
just a
2807364.
Okay, guys. Sorry. So, what is the average of? Are you guys there? What is the average of sine square theta or cos square theta for one time period? We need to know the average value for one time period, and the average of sine square theta and cos square theta, you can find this will come out to be 1/2. So you can just derive easily. So sine square theta d theta, the average we define as something like this. Huh? So average of a function is function into
Yes, sir.
d
Yes,
of
sir.
that upon this, and this we can write as 1 minus cos 2 theta by 2 into d theta, and this will go from, let's say, 0 to 2 pi, because we are talking about the one time period. So the term that we get is d theta by 2 integration minus 1 by 2 cos 2 theta d theta, and we know for cosine function for one time period this is always 0. Correct. This is always 0. So this term will become 0. So what we left with is 2 pi by 2, which is pi by 2 pi, which is. So always remember this answer. This is always half, and therefore the average value turns out to be 1/4, because this is 1/2 mu. So this is the average kinetic power. This is called the average kinetic power. And therefore, to find the energy, how to find the energy? If you know the power, energy is the average kinetic energy will be how much? Average kinetic power into time t. Energy is defined as power into time. That's a whole idea. So average kinetic energy you will get as 1 by 4 mu a square omega square v into t. And then you can also write Vt as lambda. So this is also a very famous way of writing the average kinetic energy. Like this. So there is something called the maximum kinetic energy. So maximum you can get directly from here. So the maximum will be when this is 1. So it will be half. So the way to remember is the maximum Ke max is twice the average. So Ke max is twice the average value. So you can just remember like this. And so it will be like 1/2 only. Just in case if you need to solve some question, uh, and if they ask you the maximum, just remember this answer.
Sir, in the red box.
Yeah, in the red box, the maximum is twice of the average, and average is 1/4, so maximum become 1/2. You can
Yes,
see
sir.
the code, and later on I'll give you the simple way to remember this. So generally, you're not supposed to remember the kinetic and potential separately. Just need to remember the total energy or the total mechanical energy. So now we'll talk about the potential. So potential derivation is slightly complex, and let me take you through the derivation part. So if we have a wave, this is the wave. So if you take a elementary part of length dx, then when the wave will pass through this region, the particle will be now in this state. It is like a stretched. If you zoom this out, it looks like a this. Now it's a big length ds, and earlier it was actually dx. So there is a stretch in this particle, or you can say the string. And when you deform the string, what you store is called potential energy. So If I call this as dx, you can call this as dy. So the new size of the stretch string will be under root of dx square plus dy square by Pythagoras, and this we can write dx common, so it becomes 1 plus dy by dx whole square power 1 by 2, and dy by dx is like a slope. And what I said, in case of when we do the derivation, the slope we take as close to zero as possible. So the slopes are actually very small because these are not having the very small amplitude, so the tangents are very small tangents, and therefore we can use the approximation, binomial approximation. We can write as 1 plus 1 by 2, and because it's a multifunction, so we prefer to write as del y by del x whole square, like.
So we have to square its like partial derivative.
Yeah, eventually we have to convert the dy by dx as partial derivative because y is a multi-variable function. So although we derive like this, but it can change into partial derivative without any loss of generator. So it will not create any harm to the mathematics. Now this is the new length, and this is the old length. So what is the change in length? New minus old. And if you do so, what you get? 1 by 2 del by del x whole square into dx. So this is called the change in length of the string. And if you remember, the change in potential energy is defined as minus work done by system. So here tension is acting, and the stretch is okay. Tension. If I look at the dx length, so for dx length, the tension will act this way. At this condition, the tension is acting this way. You can see clearly the stretch is happening against the force. So minus T dot, I can say dl. But what is the angle between the dl and T? It is again 180. Okay. So uh, minus internal. This is the force, external force. Okay, so we are writing the for this dx length, the T will act as the external force. So we have to make it a slight change here.
So why?
Because the tension for the dx is external force, no? So
Yes,
tension
understood.
left, right, and it will also stretch this way only, so it is supporting only. So we can write T dot dl as T dl. So the potential energy change of the system is T times dl, which is T times. Now T is not the time period; it's the tension. So better what I can do is I can just change the name. Let's call it F, just to avoid confusion. Time period and all. F. So we can write as F into 1 by 2 del y by del x whole square into dx. This is the answer. This looks, the potential energy is equals to F by 2, and del y by del x is how much? So we know y is equals to A sine omega t minus kx. So del y by del x is minus AK cos omega t minus kx, and therefore you can write as A square k square cos square omega t minus kx, and f A square k square by 2 cos square omega t minus kx. So let's consider a particle at origin. So let's consider particle at origin. So the potential formula will change as fa square k square by 2 into cos square omega t into dx. So now there are many ways of writing. As I said, we can always convert the dx into v dt. So you can write as, not to confuse you. So du by dt is the potential power due to potential, the rate at which you are supplying the potential. So du by dt is basically f a square k square v by 2 into cos square omega t. Let's call it pu. And the average pu will be how much? This will become average. So f is average of this function. And just remember the average of the function is 1 by 2. This becomes f a square k square v by 4. So that's the average power. So the average potential energy is how much? Average potential power into time. Now this will not be confusing. This turns out to be f a square k square vt by 2. Vt is gonna again act as lambda. So it is f a square k square lambda by. So this is the formula that we can derive eventually. And you need to practice a lot to actually get a hang of all this thing. So just by looking at the formula, you will never get the confidence. Practice so many times so that these method become part of your you know daily routine. So you should make it possible. So this is f by 4. Now from the equation of wave motion, you will come to know later on. I will just derive after this the next topic. So the velocity of wave we can okay. So from the definition of velocity of wave, we can write as v equals to f by, or this is like tension by mu, f by mu. This is how we write. And why I'm writing this? Because I want to write f as mu v square. Because I want to prove that these are equivalent formula. So the way you derive the kinetic and now what we are deriving, they are similar. Just look for the now timing, it's different. And therefore this becomes mu v square a square k square lambda by 4. And these are like manipulation which you have to learn eventually. So 1 by 4 mu a square k square v square lambda. Now I'm writing k v together because again if you remember omega is defined as kv. So that's why hell lot of manipulation, and that is why even I don't remember anything. I keep on deriving like this. That's how I have learned through derivation only. So even as a student, I used to derive a lot. So every time I'm solving one question, I used to go through the entire derivation. And doing it again and again made make sure that okay, I can solve any question, no matter whether I remember the formula or not.
So for this chapter,
Yeah, for this chapter is something the most difficult one. Why? Because This chapter is easy in terms of formula. If you know, if I give you the sheet of formula and tell you solve the question, it's easy. In the examination, keeping track of all formula is a bit challenging. Okay, so that is what you will learn eventually. It's challenging. So now you can see that this formula is matching the formula of potential. Same formula. So no need to derive. Just the whole idea is you're not supposed to know all answer. Just remember any one formula and you're done. So even though you don't remember the derivation, that's okay. So the potential is this much, a kinetic is this much, and once you have the formula, you can see the total energy, or you can see the E average total energy. Let's call it. Therefore, average total energy is equals to U plus K, and because they are same, so it becomes half. So this is the total energy, the average supplied per time. So this is called the total energy per cycle. So we are taking the average for one cycle actually, and it turns out to be this answer: 1 by 2 mu a square omega square lambda. And why 1 by 2? Because 1 by 4, 1 by 4 is 1 by 2. So now this is the answer. The total energy per cycle. So the word per cycle is kind of hidden. It will not be said explicitly, but it is implicit in a way. So this is the energy, and if you want to know the average total power per cycle, which we call only P. Like, I mean, this is so common that we don't say average per cycle. It's like, yeah, we understand it's average only. So we when I write P, it's P average. But anyway, I'm writing P average. So this will be equals to. So how we write the average power? The total energy, the average total energy upon time period. That's it. Because power is energy upon time. So you can just write like this. And this is 1 by 2 a square omega square lambda whole upon time period. And this is nice. 1 by 2 mu, and this is lambda by t. Okay. And lambda by t is what? That's called the wave velocity. So the average power formula is very famous: mu a square omega square v. Am I audible or not audible? Hello, 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 hello. Okay.
Hello, sir. Yes, it's audible.
So the average power, you understood the formula, how to derive this formula?
Yes, sir.
Average total power. So you can see the total power formula is 1 1 by 2 linear mass density into a square omega square. So now the most important part is called intensity. So we define here intensity as the average power per unit area. This is area basically. So I'm writing area by the symbol S. Why? Because A is already there, so I cannot use A. So A is for amplitude. So I have to change some symbol. And how to think about area? Every medium, this is the medium. So every medium in. So this is the medium. So what I'm saying is the energy will propagate along its length, right? Like
Yes, sir.
this is how the energy propagates. So these are like I'm just zooming the party so you can see. So this is called the cross section area. This is called S. The cross section area through which the energy is entering. So energy is passing through this area. That's the whole idea. And intensity is defined as that the energy crossing the area per unit time. Okay, per unit area. So the actual definition of intensity is amount of energy crossing per unit area per unit time. So here we take the intensity again we define for the average value. So this is the d by dt is like a like a power.
It is instantaneous.
Pardon? Yeah, intensity is defined for cross section, not for the medium. Intensity is the point function. Intensity represents the energy density at a point. So we'll come to that later on. Understood? Because
Yes,
this
sir.
is just a definition. So intensity is defined as like this. So not to understand the relation between the linear mass density and the density of medium, let's say rho is the density of medium. So if I choose a length dl, the mass we can write in two ways. So mu dl in terms of linear mass density, or we can write as density into volume, SDL, right?
Yes, sir.
And if you compare these two, you can see the linear mass density is actually density into cross section area. Understood? So every medium
Yes,
will
sir.
have some density, but in case of string, we prefer writing a mu. We don't write mu as a row, but nevertheless, we can do that. So intensity you can write as 1 by 2 mu a square omega square v upon s. And now we can convert the mu as rho into s. The s will cancel out, and now you have the very nice formula 1 by 2 rho a square omega square v. Understood?
Yes, sir.
So the final formula is intensity equals to 1 by 2 rho a square omega square into v. And if you try to remember, this is the a omega is called the v max, right? So
Yes, sir.
if I try to define the energy density, so let's call there is a term called energy density, and we represent by the u. This is defined as the total energy per unit volume. So the total energy per unit
So
volume.
like
So we know,
distribution of energy in the.
yeah, energy density is simply energy upon volume. So we know that how much energy is spread across a wavelength lambda. So we know if this is the lambda, this will have the energy that we have actually calculated. So how much energy we got? So you can think this way. The energy is basically the P average into time T, correct? And how to write the volume? Because this is almost like a straight line. As I said, you can always consider the amplitude to be roughly zero. So this is like a straight line. Cross section is S and length is L. So what is the volume here?
lambda.
S lambda. S lambda is the volume of the medium. Understood?
Yes, sir.
For the energy density, we can write as average power into time because this is the energy. So the energy supplied in the time t will spread over the wavelength lambda. So the energy in this part is the energy which was supplied in time t actually. Understood?
Yes, sir.
So this we can write as S into lambda, and therefore energy density becomes the power formula we know half mu a square omega square into V into T upon S lambda. And if you look carefully, Vt will cancel with the lambda because they are same, and this will become rho S. So this will eventually become half rho A square omega square. So now this is the energy density formula, which is again very important. You can see there's so many formula. You have to just take a note and put everything on your wall. You have to keep on looking at this formula every time. So very difficult to remember for any beginner, including me also. So now we have the relation between the intensity and energy density. So the only difference between these two is the missing of V. So I is basically UV. Now this is easy to remember.
Yes, sir.
I is how much? UV. And how to remember U? So this is also easy. Imagine the maximum kinetic energy will be how much? dm into V max
Max
square
square.
upon dV. Let's say this is the volume. We can write this as half rho V max square, and V max is how much?
Omega A.
Now you can see it's easy to remember like this.
So, yeah, understood.
And no, this is not a derivation. This is just a way to remember. Memory method. And so the intensity formula is pretty easy. So you're not supposed to remember anything. Just think this way. What is intensity? IUV.
Yes, sir.
Simple. So you can go the reverse process. The way I remember things is I remember the last answer, and from there I reverse to go to the all answer. So let's say I know only one answer. So let me show you how I do the question. So let's say I know the energy density because that's easy for me in my brain. Half rho A square omega square. Now you will ask me, sir, what is the energy then? So energy, the total energy will be energy density into volume, which is S lambda. So I know this answer. So you can think this way that if you have the energy density, if you multiply with the volume of the volume of up to length lambda, what you get is the total energy. Okay, that's easy. And if you divide this by the time period, if you divide with the time period t, what you get is average power. If you divide by the cross section area of the rope, you will get the intensity.
Yes, sir.
So anything you want, you can get the answer. Understand?
Yes, sir.
So remembering only one answer is sufficient. So you know the U, then you can find the total energy because density into volume is called energy because energy density. So what is energy? Energy density into volume. Understand?
Yes, sir.
So this is how you can actually derive various formula and uh, these are the only formula which you need to know. We have to derive one more formula, that's called the velocity of wave in a string and velocity of wave in a sound. That we'll do in the next lecture thoroughly.
Sir, I have a doubt in intensity.
Hmm.
Sir, the dE by dt is the instantaneous energy, no?
Yeah, yeah. So that is, see, that is the definition. So what we are defining is the average intensity. So even the intensity by default here is average value. Understood? It's like everything is average. The average intensity, average energy, because we cannot define for one instant. What we are trying to define is for one cycle.
Yes, sir.
And here the average intensity is the by default choice. So we don't mention the word average. It is like intensity when we try to define here, it is meant for the one cycle only.
Yes, sir.
So we take the average. That's the whole idea. Okay. So you can just keep in mind, or you can derive and get the answer. So this is the one part, I mean, of the wave and sound. It will take like at least 4 or 5 classes more to complete the wave and sound part also. So we have wave here and we have sound here. And in the wave chapter, the velocity is having formula, that tension in the string upon mu. This is called tension in stretched. All right. So we'll stop here. We'll see the next.
Bye, sir.
Good night. Good evening. For me, it's night because I'm always in my room, so I think it's night.